What if circuits could be made flexible? What if they could diagnose a heart attack before it happens? What if they could deliver drugs to your body and dissolve when their work is done? Thanks to John A. Rogers, they actually can. He'll tell President Aoun how he's making it happen. Join them for a fascinating conversation about integrating living and electronic systems.
Ladies and gentlemen, please welcome John Rogers.
All right, that's my introduction, okay. It's a pleasure to be here. Thank you for the invitation. What I'm going to do is spend the next 40 minutes or so telling you about some of the things that we've been doing at Illinois in the area of electronics, in particular, work around electronic materials to try to create a future in electronics that is much different than the kind of integrated circuit technology that you find around you today. And that's what I'll talk about, things that stretch and fold and integrate with your body in unusual ways, devices that can actually dissolve in water and yield biocompatible end products and things that are environmentally benign. And I'll step you through some of the different applications and the approaches that we've used. But before I do that, let me just tell you something you already know to try to place some of our work into context with things that are already out there today. And if you're an old guy like myself, you remember that integrated circuit technology and computer systems used to be huge devices, things that would take up large amounts of real estate on your desk or fill entire rooms. They were designed primarily for specialized purposes in industrial and scientific computing. And they were great classes of technology, but pretty narrow in terms of their range of application and their utility. And so that was sort of the past. And what happened over the intervening 30, 40 years is that there has been a relentless effort in miniaturization. So the individual switching elements in these computer circuits have decreased in size. It allows you to put more and more of them per unit area, each one of which can operate at higher and higher speeds. So you can take those computer systems that used to fill entire rooms, and now you can put them into a laptop computer, put it in your backpack. You can put these devices in your pocket. And that is a spectacular success at the level of the engineering and the technology. But what may even be more significant is that it allowed a real qualitative change in the way that the devices are used, from these niche applications in high-end industrial and scientific computing to devices that now permeate every aspect of our daily lives. And so they have a function that's much more personal, productivity enhancement and communications and entertainment, and that sort of thing. So that's kind of the past. That's where we are in the present. And let me say one more word about the technology driver that really allowed that to happen. And it's known as Moore's Law, and I'm sure many of you are already familiar with that, but just in case, just remind you that Gordon Moore is the founder of Intel, one of the key people at Fairchild Semiconductor, sort of brought the transistor to the commercial world, observed in the very early days of the technology that there was sort of a doubling in the number of transistors per integrated circuit component, and that doubling was happening about every 18 months. And he projected out in the very early days that you would reach levels of integration that correspond to sort of billions of transistors out into the present day. And amazingly, the industry has really stayed on that roadmap. And it's really as a result of deep additional fundamental scientific understanding around the way that the devices operate, the way to manufacture them. A lot of material science advances have enabled this. And so that's spectacular. And the consequence is what I showed you in the previous slide. It has allowed integrated circuit technology to really proliferate and impact every aspect of our daily life. So that is Moore's Law. And you can imagine extending that projection out into the future. And if you do that, then you really then sort of predict where things are going. So the Moore's Law vision of the future is just a continued miniaturization. So the transistors are getting smaller, they're getting faster, they're getting cheaper on a per device basis. And that is a compelling vision for the future. It's certainly driven a lot of progress over the last 40 or 50 years, and there's no reason to think think that that will slow down or subside out into the next 10 years, let's say. And so if you think about research opportunities in electronics, that is one, and that is a compelling opportunity because it's addressing $1 trillion global market at this point. So a lot of interesting topics in research that will be required to sort of fulfill that future. So that's the semiconductor industry roadmap. But what I want to talk to you about is a different type of future, a future not built around Moore's law, but something that's more than Moore. So not just a continued miniaturization of the device technologies, but looking at something characteristic of the integrated circuit that has not changed at all over this entire period of development of the technology. And that is the fact that every commercial integrated circuit that has ever been built has been built on the rigid planar surface of a semiconductor wafer, a disk of silicon or gallium arsenide, hard, brittle, rigid material, perfectly flat. And it's by consequence of that platform that all commercial and consumer electronic devices have that overall geometry. Even sort of an iPhone, it's a very flat thing. You can't bend it. And that's not a problem for a laptop, for a desktop computer, for an iPhone. But you can imagine there's tremendous technology there. And if you could take your iPhone and wrap it onto your brain or melt it into your skin or envelop your heart with that kind of technology, there may be opportunities for dramatic advances in the way that healthcare is done, or health monitoring, interventional science. And there, the challenge is not making the transistors smaller and faster and cheaper. It's really reformulating the electronics to look more like the human body. So instead of a semiconductor wafer plate of glass, think about a substrate that's like a thin, stretchy membrane that could sort of wrap the complex contours of the body, allow the devices to be integrated intimately with biology without constraining any of the natural processes or natural motions associated with the various organs of interest. And that's a future that we're interested in. And it's driven by advances in materials and manufacturing, but in this direction of more than more, not just more. So that's what I'm going to tell you about. We've done a lot of work on the heart, the brain, and the skin. And I'll focus on just the skin, just to give you a flavor of how the devices work. And without getting into all the detailed aspects of the technology, just try to describe a couple of very simple ideas that have been very effective for us in this space. So let me talk about wearables a little bit, and then again, sort of give you a perspective. So if you think about devices on the skin, you might immediately say, well, people have been thinking about wearables for a long time. You would be right. And in fact, the idea of a wearable electronic system predates the transistor. So if you go back, in the mid-40s, you can find pictures like this. So this was from Radiocraft magazine. This was back in the days of vacuum tubes. And this is a very interesting wearable system that someone put together, a very clever use of a hat that has an antenna embedded in it. And you got large battery packs and vacuum tubes on your belt. You got wires running around. And I think that's meant to be some kind of entertainment system at some level. But that's probably one of the earliest examples of a wearable electronic system. That's around 1945. And it really wasn't a one-off. That was kind of the first embodiment. A couple of generations later, it began to look like this. It's a little slicker, a little nicer. So you sort of integrate it in the hat. You got these big vacuum tubes. You don't know what to do with them, so they sort of made a fashion statement of some sort, like little horns there. So, again, wearable radio, pretty interesting. So what happened is, you went away from the vacuum tube, you get rid of the horns, you go into transistors, and then Moore's law is having a huge impact on the way you think about a wearable, entertainment system, such that, very, very sophisticated, iPods and things like that are now available, for entertainment. But what happened as well, though, as I argued previously, is that this relentless change in the technology not only makes things smaller, but allows you to do different kinds of things with the technology. And this area of wearables is now being dominated by devices that monitor essential processes in health that are related to health and fitness. So, I own a couple of these kind of devices. I won't go through the manufacturers, but you can make very, very small, integrated circuits and radios and sensors, and you can put them in kind of a watch format, and that's pretty interesting. And pretty much all of these kind of devices that are in this wristwatch format are measuring overall activity, just acceleration. So it's kind of rattling around on your wrist. So it's not a particularly precise type of measurement, but it can give you some useful data that relates to activity. Now, if you really wanted to measure, though, essential body processes, something that rattles around on your wrist is not particularly useful. You need to couple more intimately with the body to get higher quality data and a richer set of data related to physiological status. So if you go away from this wristwatch type format, then you get into a class of device that begins to highlight the limitations associated with that rigid planar integrated circuit topography that I mentioned to you before. So if you want to do ECG, for example, you want to measure heart rate, now you're talking about a hockey puck on a strap, essentially, and it's pressing into your body. And that can work, but you can imagine that's not the most comfortable type of device to wear long term. And again, the amount of data that you can obtain is somewhat limited. So, if you think about the future of wearables, again, the most obvious future is one that bootstraps on this Moore's Law progression. Everything's going to be getting smaller and faster and cheaper, but it's particularly in this kind of wearable systems, unless you change the form factor, the amount of data and the value of that data will be limited because the devices are so highly mismatched from the characteristics of the skin. So if you want to get more clinically useful data, then you start requiring systems that look like this. And so on the left, you have a device designed to measure and record ECG. And the design construction involves point contact electrodes taped onto the skin, attached via bulk wires to a separate box of electronics that you put on a strap and put on your arm. And the data that you can get out with that kind of system is quite high quality, but it's not good for continuous monitoring. It's great for hospital setting or laboratory setting, but these tapes and these wires, it's hard to manage the wires. You can do a few point contacts, but not a large number. You certainly can't really exploit this kind of Moore's Law scaling in electronics because the interface here is just electrodes. All the electronics are separately located. And besides that, the tape itself has mechanical properties that are much different than the skin. So it's constraining the natural processes, the natural motions of the skin, and that causes irritation over time. So if you wear these things for a long period of time, it's sort of like Chinese water torture or something like that. It becomes very, very painful and very irritating. So very few folks are willing to accommodate that kind of system. And you get a little bit more sophisticated. If you take the chips, you crack open that box, you pull the chips out, you can glue them to a tape, and make a flexible printed circuit board type device. You put that on the skin. It's a little bit better, but it's still not very good because the mechanical properties of the tape are different than the mechanical properties of the skin. So the tape can bend, it cannot stretch. The skin can do both of those things. So again, it's sort of constraining the natural motions, and it also generates interface stresses that tend to make robust adhesion difficult to accomplish. So what do you do about this? So this is a challenge and an area that we got interested in some years back, and we begin to think, sort of step back, forget about electronics for a second, and ask yourself what does go onto the skin and works well. And we decided that a kid's temporary tattoo was a great model for a kind of technology you could put on the skin because you can put it on the skin, it looks great, and then once it's there, you don't even know it's there because it doesn't constrain any of the natural motion. So the skin can move around, but there's no mechanical or mass or thermal loading associated with the tattoo. So we decided, if you could make a piece of electronics that has the physical characteristics of a temporary tattoo, that could be a pretty useful thing. And what are those properties? You want something very, very thin, so maybe 5 microns in thickness, maybe 1/10 the diameter of a human hair, 20th of the diameter of a human hair, something in that range. Very lightweight in an aerial mass loading sense, so maybe 1 milligram per centimeter squared, something in that range we thought would be a good target. Very low in modulus, so the stiffness of the device is very, very low, 5 kilopascal we thought would be a good target. Turns out the skin can stretch by about 30%. So if you wanted to make a piece of electronics that accommodate the full range of motion of the skin, 30% stretchability would be something to think about. Devices that can accommodate transepidermal water loss, so need to be air and water permeable. and at the same time waterproof, so you're not getting unwanted electrical contact between your devices and the skin. So those were the things that we decided would be attractive in electronics. And so if you look at those characteristics, you might say silicon is out, because silicon is a very stiff material. How are you ever going to get it into this geometry? And you might say, well, you have to go to a different class of material. And we had thought about that type of strategy. At the same time, there's just tremendous base of knowledge and manufacturing infrastructure already built around silicon. So the point would be that if you can do that with silicon, that's the way you're going to do it. So we begin to focus a little more on silicon and ask the question, is silicon inherently incompatible with this set of characteristics? And if you think about silicon in the form of a wafer, the way it's always been used for integrated circuits, you might conclude that it is fundamentally incompatible because it's planar, you can't bend it, it's very fragile, it's a brittle material. But it's really, it has those characteristics partly because the intrinsic properties of the silicon are such, but it's also because the wafer itself is fairly thick. It's about a millimeter in thickness. And if you think about the mechanics of bending of any kind of material, it's dependent not only on the intrinsic material properties, but also the geometry. If you think about a 2x4 compared to a sheet of paper, 2x4 you cannot bend it, sheet of paper you can. It's the same material, it's just by virtue of the fact that the paper is very thin that it becomes flexible. The same thing applies to silicon. So it's a very elementary principle in any kind of bending mechanics. And so the question is, could you generate silicon at thicknesses that are so small that it becomes flexible? Now, the way that a silicon wafer is created is you grow a boule, sort of a cylindrical piece of silicon, and then you slice it up to form the wafers. You cannot use a mechanical saw to slice silicon thin enough that it becomes flexible, but you can use specialized etching tricks to slice off of the near surface region of a wafer very, very thin slivers or membranes or ribbons of silicon at thicknesses that yield sort of a mechanical floppiness in terms of the bending mechanics. And I won't go through the details, just to make the point that you can then, and we sort of figured this out, take a silicon wafer and then use kind of an anisotropic etching technique to allow you to slice off the near surface region, very, very thin elements of silicon, and you can even slice off the near surface region, not just the silicon, but also the devices that you build on top of that silicon wafer. And as you can see in these electron micrographs, at that type of thickness, the silicon is very floppy. And so we figured that might be interesting and a kind of mechanics that you could exploit for these skin integrated devices. But silicon that's thin is flexible, but it's still not stretchable. There's no degree to which you can thin silicon that will allow it to stretch. It just becomes easier and easier to flex. But I've already told you that the skin not only flexes, it stretches. Same thing with the heart and the brain. If you have a material that just flexes, then you can wrap a cylinder or a cone, but you can't even wrap a sphere, much less a heart or a brain or the skin. So you need another idea to add on top of this notion that thin silicon is flexible to achieve stretchability in the silicon. So that's idea number one, make the silicon very thin to make it flexible. Idea number two is to take that thin silicon and bond it to a rubber substrate. Now the rubber gives you the elasticity, and that's important for these kinds of applications. But if you stretch the rubber a little bit just before you bond the thin silicon to it, and you relax the pre-stretch after you've done that bonding, what happens is the compressive stresses on the silicon yield sort of a buckling process that creates a wavy geometry in the silicon. So now you have a very thin, wavy sheet of silicon, hard material, on a very soft rubber substrate. And by virtue of that geometry, you can achieve sort of an end-to-end stretchability in the silicon without cracking it, because it responds in much the same way as an accordion. So the physics is very similar. You stretch it, the amplitudes of the waves go down, the wavelengths go up. And the reverse happens when you compress it. The amplitudes go up and the wavelengths go down. So now you have an overall elasticity in a material system that integrates silicon. So those are the two ideas: make it thin, structure it in this kind of wavy geometry. Now you can make silicon that stretches back and forth like a rubber band. That's kind of what we wanted to do. Now that is not an integrated circuit. That's just a couple of ideas in material science. It turns out that if you take those two concepts, you can add sort of engineering elaboration on top of those ideas and do things that really do have the characteristics of that kind of temporary tattoo that I mentioned to you before. So I won't go through all of those details. Just make the argument that those two ideas can be embodied at the integrated circuit level. You can exploit not only this kind of out-of-plane waviness, but you can also create an in-plane serpentine geometry, so you get buckling both out of the plane and in the plane. And you can interconnect that type of system into an integrated system that you can laminate onto a thin sheet of an elastomer that can then be integrated with the skin. And that's what you're seeing in this view graph. So this is a full piece of silicon integrated circuit technology on the surface of the skin of the postdoc who built this device. And then we came in with like a glass rod and poked them a little bit so you can see sort of how it deforms. And the point is that the skin is not constrained in its natural motions by the presence of this silicon integrated circuit at all, because the entire system is engineered to offer this soft elastic mechanics. So that's what it looks like. If you grab it by an edge, you can easily peel it off. So this thing is just clinging onto the surface of the skin, not with any separate adhesive. It's just a slight tackiness in the silicone rubber support. So you peel it off. And the right frame there gives you a sense of what it looks like when you have peeled it off. It's so thin and stretchable that it collapses under its own weight. So it sort of droops down like that. Now that's giving you a sense of the mechanics and the physical properties. You might ask, how in the world are you going to even handle it and manipulate it to allow mounting onto the skin? And for that purpose, we just went back to the world of temporary tattoos and figured that you could just use similar ideas there. So we use a water-soluble plastic tape as a handle for the device. So you can take that device then supported by this water-soluble plastic and then laminate it onto the surface of the skin. And then as you wash away that water-soluble layer, you leave behind just this kind of soft skin-like or epidermal electronics clinging to the surface of the skin. And so that's what you're seeing here. The device is laminating onto the forearm, again, of one of the students who's working on this project, and he's just applying a little bit of water with his forefinger to that water-soluble backing layer, slowly dissolving it away. And once that's completed, then you have a system consisting of the skin, the epidermal electronics in direct contact with the skin, and then on top of the epidermal electronics is a thin silicone elastomer sheet that's transparent so you can see through the whole thing. So that's what it looks like. It's now on the skin, and if you pinch the skin, then you get a sense of the mechanics. So the sort of the bright, shiny region there, that's the silicone, extends out beyond the region of the circuit. But as you pinch the skin, you can see how the circuit deforms along with the natural motions of the skin in a way that's not constraining the motion at all. So in that sense, it's mechanically invisible. It's on your skin, but you don't notice its presence because the mechanical properties are really matched to the epidermis. This particular platform includes an array of silicon transistors, diodes, inductors, capacitors, LC oscillators. There are temperature gauges, strain gauges. There's an RF antenna and a wireless inductive coil for power transfer. So that's what it looks like. As I mentioned, it's just held there by van der Waals forces, so no penetrating pins or adhesives or straps or tapes. So you can simply grab it by an edge and peel it back when you're done. And so that's what you're seeing here as it peels back. It sticks a little bit more right there at the upper right edge for some reason, eventually comes off, and you can see sort of what it looks like. So it's integrated circuit technology that has a slightly disgusting appearance, to be frank. So it looks very much like skin. So it's on there, but it's not on there all that well because it's just this tackiness. Now, if you want better bonding, we figured, why not just use an actual temporary tattoo? It already has FDA-approved adhesive in there. We just put the circuit on that and then laminate it right onto the skin the same way you would apply an ordinary tattoo. So we created this custom Illinois Pirate here. As a demonstration vehicle. So there's a circuit beneath the temporary tattoo in direct contact with the skin. And here we're using that built-in adhesive to do things. So you can't see the circuit. That turns out to be an interesting feature for certain folks who would like to use this technology, sort of covert communication devices and so on. You also do get the adhesive, so it's a more robust bonding. This is, as I mentioned, a custom tattoo. Illinois doesn't have anything to do with pirates, but we figured, tattoos and pirates somehow go together. And it turns out that if you order a custom tattoo like that, the minimum order is 1,000. So we only needed about a dozen of these for our experiments, so I brought with me some of the tattoos, and I'll give them away, anybody who wants them. There's no electronics on here, unfortunately, but you get the special custom tattoo if you're interested.
Do you have any Spider-Man ones?
any one you want. We sort of like the pirate. So that's what it looks like. Let me give you an idea of what it sort of looks like at the microscopic level. So this is a surface of a piece of plastic that's molded in the geometry of naturally occurring skin. You can see the skin is quite rough and textured at this length scale. But this kind of spiderweb geometry and the ultra-thin layout and the buckling and so on really allows a very good conformal contact. So that leads to good adhesion, but also good electrical coupling and good interface to the skin. So the skin is sort of a window into intrinsic processes of the body, and it turns out to be a good location for doing physiological status monitoring. Now, because the devices are so thin, unlike tapes and wires, you can really put them anywhere. And so, if you're a student in my group, you get a chance to put these devices all over the place. Here's some pictures of places, at least that I know of, that the students have put these devices. So, forearm, jaw, and finger, and back of the neck. Depending on where you are on the body, you can use the electrical interface to measure processes of the body. So what this is showing is basically electrical activity associated with contraction of the skeletal muscles in the jaw and the forearm, back of the neck, and the finger. You can put it on the chest, for example, and you can measure ECG, sort of clinical quality ECG, so you can see the QRS waveforms associated with beating of the heart. You can put it on the leg, and so you can measure muscle activity associated with walking, and so you can measure gait, for example. You can also put these things on the forehead, and you can measure brainwave activity. So you might imagine this type of technology serving as the basis for brain-machine interface, controlling prosthetics, for example. Because you can put these devices on regions of the body that sort of outside of the bounds of what you could accommodate with tapes and wires, we figured that brain waves would be one way to do machine control, but more generally, thinking about a human-machine interface, you could use other parts of the body, and in particular the neck is interesting because there's a lot of fine motor control associated with speech. You put these things right on the neck, and you can measure that electrical activity during speech, and you develop different patterns of electrical activity associated with different words, either vocally or subvocally stated. And we work with experts in pattern recognition technology. You take that data and you can bend it. So you develop a learning algorithm so you can develop a command system based just on muscle control in the neck. So you might imagine if the folks who suffer from diseases of the trachea, for example, this could be relevant. If you want to control a prosthetic, that would be another opportunity. My students were more interested in playing video games, so we showed that you could do that as well. This is just a strategy game, so you move the green cursor up, down, left, or right just by saying up, down, left, and right. So if you want to play a video game with your neck, we have the technology for that now. It's very exciting. That was an initial demonstration sort of done just in software, so a little bit slow. You couldn't do an action game. But since then, we have developed firmware approaches to do this. So this is sort of more real-time demonstration of gestural control of a remote control helicopter. So the postdoc in the back, sort of the center of the screen here, has two of these devices, one on each forearm, and we've developed codes that will allow him to execute a series of commands by moving his fists that will allow him to control the helicopter. So the rotation of his fists sort of in a clockwise direction corresponds to the command to take off. He tilts his fist to the left, and that will cause the helicopter to rotate clockwise. He can stop that rotation by coming back to the center. Clenches both fists, that corresponds to a command to fly. He releases the clench, it'll stop. He rotates his fist in the other direction, it will land, go, spool it up the other direction, it will take off again. He'll tilt his fist now to the right, and the helicopter will start rotating counterclockwise. He can stop that rotation at any moment. He'll stop it now, and then clenches his fist again. And what he's trying to do is he's trying to fly it back such that it will land in that box where he started. So he'll spool it down again, and as you can see, he missed. So he might need some practice, but you get the idea. There's not a lot of reason to continue with that. So that is a set of ideas in material science allow you to do things on the skin in ways that were previously impossible. So the style of research that we do is really focused on academic demonstrations of new ideas, but we also look for opportunities to translate things out of the lab and into the real world. And we have set up a company called MC10 to serve as a vehicle for doing that. And some of the Northbridge folks are here. They're key investors and supporters of this. MC10 launched its first product in the summer, and I brought a couple of them if you wanted to take a look at this. This is, to my knowledge, the first example of a device that really has electronics in a fully flexible package. And what the device does, and it's sort of co-marketed with Reebok, is that it integrates with the skull through a skull cap. So the device sort of threads into the brim region of a soft good that Reebok makes, and you put this on your head. And the soft good and the flexibility of electronics allows mechanical coupling of the device to the head. And there's precision accelerometers and gyroscopes here that allow the detailed physics associated with an impact that's suffered to the head to be recorded and transferred to a base data acquisition system here that has sophisticated algorithms that interprets this data and bends it according to categories that establish the severity of the hit. And so it turns out to be an important type of capability, especially in the context of concussions that are happening more and more frequently these days in football and lacrosse and hockey. And it really provides additional data to help coaches and parents and healthcare professionals to decide what kind of action to take following a hit to the head. So this is available since the summer. You can go to the web and order it. So I'm not a salesman, but I recommend you strongly order early, order often. We're trying to move product here. So this is a very, very nice device. I highly encourage you to take a look at it. So that's one example that gets us on a roadmap, to this fully epidermal type of electronics, a very exciting development recently. So that's one specific opportunity. Lots of other things you could do in sports and fitness. I think my own research group is a little bit more focused on healthcare, advanced healthcare. And here's one example of something that we are thinking hard about these days. So I mentioned to you the hassle of these wires and these tapes and stuff like that for adults. And you can imagine what it's like for premature babies, which require a lot of monitoring, an intensive care unit. So it's not just a hassle, it's a really compelling sort of situation that you could think about addressing perhaps with epidermal electronic ideas. So this is current. That's what we hope the future would look like. And no, we have not put devices on babies. That's just Photoshop. So but that's where we want to go. And we think I have a lot of the ideas and capabilities in place. I think that's going to happen very, very soon, that type of device technology. So for that type of system, you really need full wireless operation. And we're working hard on that. And one of the projects that we're doing that involves a wireless interface involves some work with Google. And they're interested in data systems that can be integrated onto the skin for authentication and security purposes. And so I won't go into the details here, but this is a fully functional wireless electronic system that goes onto the skin. There's our friend, the Illinois pirate, and allows you to transfer and recover data from the skin. I'll show you a movie of that. So this is one of these devices, and the postdoc is just showing that you can sort of deform these things and at the same time write and read data from the device in purely wireless fashion. So that's a nice milestone for us and represents another building block, for the kind of healthcare applications I mentioned to you before. So the first time I showed that movie to someone, they asked me, "That's pretty cool. You can squeeze the data out of these devices. It's very nice. It's not an essential aspect. We're just showing that you can accommodate deformation and still have it work." So those are the ideas, some of the things that we're doing in skin-integrated electronics. You can imagine the same concepts being useful for devices that would go onto internal organs. And so we've done a lot on devices that go onto the brain and can measure electrical activity associated with epilepsy, devices that can envelop the entire outside surface of the heart, measure electrophysiology, can also stimulate very sophisticated forms of pacemaking, can be accomplished with that kind of geometry, full 3D membrane. So I think the ideas have a broad range of utility in healthcare and interventional medicine. Okay, so for the last 10 minutes or so, I'll shift directions a little bit, and to do so, let me come back to this slide that I put up earlier in the talk to just kind of set the context. So this is Moore's Law future, and I described what that is already, and what we're trying to do around looking at different mechanical properties and geometrical capabilities in integrated circuit technology. The other thing that has not changed with integrated circuits, besides the geometry and the form factor, is the fact that all engineering efforts to this point have gone into designing devices for infinite reliability. So devices whose properties do not change at all over time. And in fact, that capability is one of the key features that led to the adoption of the transistor and the replacement of vacuum tubes. Vacuum tubes require a lot of power. They don't last very long, whereas transistors are purely solid state in their operation. They don't involve any kind of mechanical parts. They don't involve vacuum. And so you can, in fact, engineer them to last essentially forever. And that's great for lots of kinds of devices, but think about devices that go into the body. Some of those devices would be great for them to last for a long time, but some of them you really only need over a time span associated with a transient event that's happening in the body, wound healing, for example, or you're treating a cancerous tumor. Once the cancer is gone or the wound is healed, you might not need the device anymore. If the device is designed to monitor and provide some kind of therapy associated with those processes. In that case, you might want the device to simply go away, because once the wound is healed, for instance, you don't need the device anymore. It being left behind just represents unnecessary device load on the body. So in that case, you might want something that's the opposite of infinite, long-lived, reliable operation, something that operates reliably and then completely disappears. Another example would be in the world of consumer electronics. Moore's Law is causing such a rapid change in technical capabilities in integrated circuits that although the cell phone, the guts of it, can last for 50 years, nobody wants to keep their cell phone more than about 2. So you have a tremendous problem emerging associated with hazardous waste streams associated with recycling the electronics. It might be interesting to be able to build an integrated circuit that lasts for 2-3 years, but at the same time could be very naturally degraded into the environment or composted, for example. So that has really driven us to think about different type of electronics, bio or eco-resorbable electronics. So integrated circuits that are made out of materials that are water soluble and have benign end products from an environmental and a biological standpoint. And that class of technology, you can imagine that it's actually broader than just biological or environmentally resorbable. We refer to it as transient electronics in the sense that it's any kind of electronic system that can dissolve or resorb or otherwise physically disappear at programmed rates and at triggered times. So it's really trying to think about electronics in a completely different way, where time becomes an engineering variable around the system definition. So if that's your goal, what is it good for? I've already told you 2 things, number 1 and number 3. So implantable devices go into the body and operate almost like a pharmaceutical, but with an electronic function. So you can think about it almost like an electroceutical. It could be used individually, or it could be used in conjunction with traditional drug therapies. But the key characteristic is an ability to completely resorb and disappear into the body after it's no longer needed. I mentioned this goal or idea of zero electronic waste, consumer electronics. Number 2 would be the idea of being able to distribute electronic monitors into the environment at very large numbers to monitor the evolution of chemical spill, for example. Once the spill is remediated, don't need the monitors anymore. It'd be nice if they just resorbed into the environment. So those are 3 things that we think a lot about. There's a 4th area of application that I can't tell you anything about, but that's where we receive all our funding almost these days, and all kind of military systems you might imagine. And so there are a lot of opportunities there as well. So if you think about that kind of electronics, it's again sort of a materials challenge. And if you think about the platform for integrated circuits that exists today, it's a silicon wafer. And most people think of that object as a rock, essentially, right? It's a class of material that's not changing in any rapid way. You can put it in a bucket of water, and you're not going to see anything change with that over even very long periods of time. So people normally think about it as a material that is not water soluble. So if you want to do transient electronics, you've got to think about different classes of materials. But for the same reason that we've thought hard about silicon in the case of biointegrated devices, skin integrated devices, I think here if you can do transient electronics with silicon, that's the way you would do it, because you would bootstrap off of an existing manufacturing base and base of scientific knowledge. So it turns out, and this was sort of a random discovery because we were doing a lot with thin silicon because it's flexible, is that if the silicon is thin enough, then reactions that you would ordinarily ignore become important relative to the total thickness of the silicon. And in particular, silicon does in fact react with water at physiological conditions. It just reacts with water so slowly that people typically ignore it. But if your silicon is so thin, even a very slow reaction rate could be significant. And in fact, if you look at these silicon sort of membranes that we're using for our flexible electronics, you put those in water, and if you wait 2-3 weeks, it's completely gone. So it's being dissolved at a rate of 1 or 2 nanometers per day. That's not significant at the scale of a wafer, which is a millimeter thick, but for these very, very thin sheets of silicon, it can be very significant. In fact, it could lead to the complete consumption of the silicon just in a few weeks. So you can sort of measure this. The other point to note here is that the product of that reaction is silicic acid, SiOH4, which is naturally occurring in the body. It's naturally occurring in groundwater and ocean water as well. It's biologically compatible. It's environmentally benign. And so this was a very, fortuitous set of circumstances, because it means now that you can build water-soluble electronics with high quality by virtue of the ability to use silicon for that purpose. But it really has to be thin silicon. We just drive that point home. If you think about silicon at a 35 nanometer thickness, dissolution time, you can measure this, is about 10 days. You only need about 0.5 milliliter of water to completely dissolve a 1 centimeter square area of silicon in that thickness. If you compare that to a silicon wafer, 1 millimeter thick, just extrapolate, you find that the dissolution time is nearly 1,000 years, and you need 10 liters of water to dissolve even a 1 centimeter square chip. So silicon chip in the body doesn't make any sense. Silicon nanomembrane in the body will disappear on relevant timescales. So it turns out you take silicon. There are a lot of different options for metals that are biocompatible, water-soluble, dielectrics. We use silk from silkworm cocoons as substrates and encapsulation layers, so you can actually make high-quality electronics now that are completely water-soluble and built out of materials that are known to be biocompatible and environmentally benign. So you put all those things together. That's an example of a Colpitts oscillator, sort of radio frequency building block for communication devices. And I won't show you the electronic properties. So this is a video that we developed for DARPA. You can imagine, you drop something in the field, and in this case, the rain comes down, simulated, of course, and the circuit will dissolve very quickly. You can change the composition of the materials, the packaging, and control that dissolution rate to pretty much whatever you want. So I mentioned this idea of an electroceutical. What specifically would you want to do that has relevance in clinical medicine? And this was an opportunity that was highlighted to us by one of our collaborators, a prominent interventional cardiologist at Sarver Heart Center, University of Arizona. So the idea is that when you currently go into the hospital for a surgical procedure, you're released from the hospital. One of the leading causes for readmission, need to be readmitted into the hospital, is an infection that develops at the surgical site. And a lot of times those infections are driven by bacteria, and a lot of those bacteria are becoming more and more antibiotic resistant. So the idea is that if you could drop into the body cavity at the tail end of a surgery just before the patient is sewn up, an electroceutical device made out of these transient electronic materials that could sterilize the wound site over time to eliminate an infection if it did occur, that could be a useful type of technology. So this is an example of one of these appliques, electronic appliques, goes into the body. It provides a way to heat locally the corresponding region of the body by wireless delivery of power from an external coil, and that heating can be sufficient to kill bacteria. Now, the overall lifetime of the device is set to be about 2 weeks, because it's known that if you don't develop an infection in the first 2 weeks after a surgery, your chances for becoming infected are very, very low because the wound has already healed. So these devices last for about that time frame and then naturally resorb into the body to eliminate what would otherwise be unnecessary device load on the system. So that's one example. These things can go into the body. They're biocompatible compatible in that sense. One final thing to note about these particular systems is they're not only compatible with insertion into the body, but they're edible. And not only are they edible, they actually have good vitamin content. If you look at one of these devices, it has magnesium and silicon mostly. And the amount of magnesium and silicon is not that much, about 100 micrograms and 3 micrograms. If you look at the elemental content of a typical multivitamin, one-a-day vitamin, it has about 3,000 times more magnesium and more silicon. So it's not a great vitamin tablet, but it does have vitamin value. And so you might ask, if you're doing research on this, have you tried it out? And I have, in fact. I have eaten one of these circuits before. I'm only going to do that once, and it was really on a dare from the DARPA program manager who were funding our work. And I did this at an IEDM conference, at the end of 2012. So, it goes down, it's no problem. It doesn't really taste like chicken. It doesn't taste like anything, actually. Just it is, in fact, edible, though. So with that, let me just conclude. I tried to give you a sense of a couple of futures in electronics that are different than Moore's Law type scaling, where we're trying to build systems that integrate with the body in ways that are impossible with conventional integrated circuit technology. And this second piece is trying to develop semiconductor devices that are water soluble and environmentally benign. So this is transient electronics. So with that, let me acknowledge senior collaborators who've worked closely with us. Our expertise is in material science. We want to do things in biomedicine. We work with experts there. Do things in brain-machine interfaces. We work with experts there. It's been a good way for us to make progress. So a number of different senior investigators. The most important people, though, are the students and postdocs who actually do the work. So I should conclude by acknowledging their contributions. I just get to talk about this stuff. They actually do all the work and come up with a lot of the best ideas. So let me thank them again for all of their diligence and hard work, and thank you for your attention.
We're delighted to have you here, and at some point we're going to have discussions and questions, and Josh will ask some questions that he had from the web, and we're live. So, you said something when we met that surprised me. You said, my research is not successful yet. And I said, what do you mean by that? And you said, it hasn't been fully commercialized yet. And, in academia in general, you measure success quite differently, by your funding, by your publications, by the impact, citations, etc. Your approach is very different. Could you elaborate on that?
Well, I think it's a particular style, I guess, that we have, in our own research program. And I wouldn't want to make a sort of a overall qualitative judgment of what's better or worse. I think we like to blend basic scientific research with technology development. And for the science, I think increasing a base of knowledge represents a form of success. But for us, if you can develop that scientific knowledge in the context of a technology that can have a broader societal impact, that would represent the ultimate level of success. And so that's kind of how we think about things. It's sort of I would say, a kind of a Bell Labsian approach to research. It's not research purely for basic scientific value, but research that's guided toward addressing grand challenges, right, for humanity. And so we like to think about healthcare and energy. Those are two areas where we spend a lot of time. So that's the ultimate success. There are other kinds of outcomes that are valuable. Obviously, the knowledge, the training of the students, the publication of the papers, getting the ideas out into the broader community. But the ultimate success for us is commercialization. We've had a number of successes over the years. I think transient electronics is a little bit earlier in terms of the cycle of development, but we have high hopes for broader impacts there as well.
And speaking of Bell Labs, you told me you worked there and then you moved to academia. What's the difference between the two different cultures, approaches, and the limitations of each and opportunities in each?
Yeah, so Bell Labs was a fantastic experience for me. I think I would still be there if everything were the same as it was when I went there. It's a very problem-rich environment. It's basic science, but within the context of an engineering company that's trying to make devices that can aid in communication systems. So I think the connection is very natural between the science and the engineering because of that overall construct. Universities don't have that as a natural aspect of how the system is set up. So it's really, becomes incumbent on the individual investigator to establish those ties into big companies or to kind of get involved in startups to get things from the academic research lab, again, sort of out into the broader world. So it's a different arrangement. At Bell Labs, you had world experts in every area of science and technology you could imagine, all under one roof. That stimulates a lot of collaboration, allows you to move into new fields of study very effectively and very, very quickly, sort of in a timing sense. But university is different in the sense that education becomes a big part of what you're trying to do. Classroom education certainly, but maybe even more relevant to what we're talking about now is sort of graduate student education, postdoc education. You're trying to change train the next generation of researchers, and I think there's a tremendous amount of satisfaction, at least for me personally, to be engaged in that type of thing as well, which is not a core component of what you find at Bell Labs.
Okay, so Josh, why don't you start? For those who want to ask questions, please, we have mics because you're live. And Josh, the floor is yours. You have a mic?
I do not. No.
You don't have a mic. We have a mic on this side, so another one on this side. So if you are interested in raising a question, asking a question, please raise your hand. Go ahead, Josh.
Okay, we have 3 questions from Twitter.
No, start with one, Josh. Okay. One after the other. And we'll do only one, then we go to the floor, or I'll inject questions. It will give you time to relax a little bit, then we'll have another one. Okay.
Your technology has many potential applications beyond just healthcare and training. Can you elaborate on some of these, in particular its potential for alternative energy applications?
Yeah, so it's a good question. I think it is, we view it as sort of foundational technical capabilities, and then what you do with it, in terms of specific applications, depends on your point of view, your perspective, and your set of priorities, right? So we actually got into this area, when we were thinking about display technology, sort of flexible paper-like displays would be another opportunity for this type of approach. I think over the years, we've decided to focus on health and energy. I'll talk about energy in a second. Partly because I think you get older, you start worrying about the grander challenges, not so much things in the commercial consumer electronics world. That's one of them. The other thing is you find that the students really have a big impact on the trajectory of your overall research program. Mm-hmm. And my experience is that the students are passionate about health and energy, and so over time I think we've moved in those directions for those reasons. So I've talked about healthcare. We do have significant activities in photovoltaics as a source of renewable energy at sort of the utility scale. So we have a company, they have a pilot line that's operating in the RTP area. They make the world's highest efficiency photovoltaic panel with conversion efficiencies of right around 37% at the module level. So we're quite excited about that. We have deep interest and a lot of activity in that space. And so a lot of these concepts do have utility in things outside of healthcare. I just focused on health today.
I see the folks at Northbridge are really interested in a second company. So let me ask you a question. Why is the company here? MC10.
As opposed to Urbana-Champaign?
As opposed to Urbana-Champaign or Chicago or the Bahamas.
Well, a lot of reasons for that. I can start with some comments about Urbana-Champaign. I think University of Illinois is a fantastic place to do research, one of the best environments in that sense that I've ever been a part of. It's a small town, and it's a university town, and I think it's a great place to incubate companies. It's becoming a more and more attractive place to grow companies as well. But Boston has an incredible array of sources of financing, business talent, technical talent, just an incredibly developed ecosystem that has been put into place over some decades, and I think Urbana-Champaign is kind of early in the development cycle by comparison to kind of what you have here in Boston. So that's the reason. I think a lot of it is driven also by personal connections. I spent a lot of time here, so I have sort of a network, and Some of the partners at Northbridge I've known for a long time, dating back to my days as a postdoc at Harvard. So it's a collection of considerations, ranging from basic infrastructure, what's available here in Boston, to sort of personal networks.
I was interested to hear that when you were in Cambridge, when you wanted to start a company, you used and you worked with co-op students, and now still MC10 does it. So what do you find in them? Why them? Why a co-op?
Yeah, so we've been involved with a couple of companies that have been located in the greater Boston area. One that was launched as a result of my PhD work in semiconductor metrology, is basically laser-based approaches to measure thin films that are used in integrated circuits. That was located out in Natick, and then most recently MC10 is making these wearable devices and impact monitors and so on. Both of those companies have benefited tremendously from co-ops from Northeastern, quite frankly. And it's a great way to add technical talent and technical bandwidth to a company quickly without necessarily making a longer term commitment to an individual. So you can staff up quickly, and you can sort of ramp down depending on the particular needs and where you are in the development of the company. Our experience is that the students as well are really talented, high energy. They're young kids. They're not jaded, they believe anything is possible, and they've just been tremendously effective for us, both in the context of active impulse systems about a decade ago and more recently at MC10.
Great. Josh, why don't we go? Do I see any hand? If you want to raise a question, raise your hand so we don't have delay time. Go ahead, Josh.
Okay. The market has already seen many technologies for tracking health. People argue that the next step should be more evidence-based research on the actual outcomes, and what will MC10's technologies help? Will MC10's technologies help achieve that goal?
Yeah, so that's a really outstanding question. So I'm a technologist, material science, electrical engineering guy. I am not a clinician, or medical doctor by any means. So I think the question is really going to the issue of what do you do with the data? So we think we have a device platform that allow you to collect clinical quality data, multimodal in terms of the measurement capabilities, continuously while you're at home, while you're at work, while you're working out. And the associated question is, what do you do with all that data? It hasn't been available in that form before, so I think it's an open-ended question. I think there are some instances where it's very clear what you would do with the data. There's well-known algorithms for assessing the waveform associated with an ECG recording, for example, to determine the onset of an arrhythmia or cardiovascular health issue. So there are a lot of things I think that we'd be able to do in an immediate, straightforward way. But I think it opens up a whole set of new opportunities, right? You're going to have a tremendous amount of data. Over time, I think that data will, you will establish a closer and closer connection to that, between that data and problems in clinical health. So I think the utility will only increase over time as you get more and more sophisticated in how that data is processed and mined for information. So I think there are a lot of low-hanging fruit. We'll do that immediately. You can measure, Parkinson's, tremors and things like that, immediate, right? But how you could use it in more sophisticated ways, I think, represents a tremendous opportunity. And that's going to be evolving and developing over time as this data becomes more and more widely available.
Great.
Mr. John Rogers, my name is Miles Netherton. I'm a student here for the College of Media and Design. I gotta say, I'm very impressed, very interested in the nanotechnology you've developed with the biointegration of these patches and everything. I would just like to know, what were your early inspirations to becoming a scientist? What drew you? What was your original fascinations about that made you the man today?
Great question. If you can give the mic back to Josh. Raise your hand in case, Okay, we have a hand here on this side, so go ahead.
Yeah, so I think it's a good question. I don't engage in a lot of introspection, so I don't have deep philosophical answer to this question.
I love that.
It's just kind of, I think, one of the big challenges in developing your career is figuring out what you're good at, right? And then focusing on that, and I think, my dad had a PhD in physics, so it was always, part of household discussion. Science was a big part of that. I think, he's a little bit more of a fundamental, physicist in terms of his mindset. So I would say, my initial, career path was more just in basic research, right, in physics. But I think I came to MIT That was early 90s. I think it was just the time when, students were thinking about entrepreneurship and technology and startups and, devices and stuff like that. And I think, my interest kind of shifted in that direction, maybe by consequence of the environment that existed at MIT in those days. So we entered, the business plan competition was a brand new thing in MIT at those days. We hooked up with some Sloan students, wrote a business plan, started a company. And at that point, I was hooked, and I think at that stage, I sort of knew what I wanted to do. I went to Harvard and worked with George Whitesides primarily because he was an accomplished entrepreneur and figured out how to bridge science to technology. And I thought he was a great mentor and a person to learn from. And so when I left Harvard, Bell Labs was absolute perfect place for me at those times because for the reasons it's just blending science and technology and allowed sort of fast track translation of scientific knowledge into devices. And so that was great. I mean, I think coming back to the university, we figured out how to do that in a university context. And so I think you figure out what you're best at, and then you do that, and that's kind of a process. It took some years, but that's where we ended up.
Yeah, John's wife is also a scientist, and his child is 11 years old, and are you hoping for a PhD in the sciences too?
He should do whatever he wants to do.
This is not only live, but it will be in the archives, so they can find that. And when he decides to go into something that you don't want him to do, then we will see.
I've given him permission now.
Andrei Ivankin, Department of Physics, postdoc. I have technology question. So with these devices, how do you power your circuits, and for how long can it last?
Yeah. So power and wireless communications are two of the biggest challenges in these kind of devices. You think about, with this type of thin geometry and these type of mechanics, how do you do batteries, right? And unlike Moore's law, which has had a transformative and incredibly rapid impact on integrated circuit technology, you don't see that kind of improvement in battery technology. It's just not happening that quickly. So there are sort of fundamental limits in the physics and the chemistry of how energy storage works, that it's unlikely that batteries are going to emerge that have these type of properties. So we like wireless approaches. The device that we developed with Google, I showed you, it involves an inductive power transfer from an Android phone onto the patch. So the patch doesn't have any power, but it receives power from the phone, which has the battery in it. That's kind of a near field power transfer approach. So you can do it over a distance of maybe centimeter. If you want to do infant monitoring in an ICU, it's probably not realistic that you scan the infant with a phone periodically. So there we like far field RF power transfer. So if you think about your cell phone, when you make a call, there's hundreds of milliwatts of RF power coming out of the phone. And so we have approaches that allow you to harvest that energy in this patch geometry and use that power to operate a radio that can then transmit back out. So we have that. So we like wireless approaches. It turns out that you can do batteries. The way that you do batteries is instead of having a monolithic cell, you split the cell into many tiny pieces, and then you interconnect them with sort of deformable wiring, and you develop an overall system that can be thin and stretchy. But still, the total amount of power that you can get out is going to be limited by the total volume of the aggregate collection of those tiny battery pieces. So those are the kinds of approaches we've looked at. For implants, you can, in certain circumstances, harvest energy from the body itself. We like mechanical motion and piezoelectric devices that allow you to harvest some fraction of the mechanical motion and convert it into electrical power. So we recently published a paper that involves a device that goes onto the epicardium. As the heart beats, it creates power output from the device at levels that allow you to operate a pacemaker. So you can make the battery go away in that context. But that's a pretty special context. If you imagine a patch on the arm, there's just not enough frequent motion to do things in that way. So wireless mechanical energy harvesting and sort of distributed micro batteries are three approaches that we found to be effective.
Thank you. Vince?
John, I'm Vince Harris from the ECE department. You had mentioned just now about using metallic wires, and my question is, what do you use in other issues of toxicity, and how do you deal with that?
Yeah, so two questions. I mean, we can use conventional metals in these skin-worn patches because the metals, except for cases where measuring electrical activity of the body, the metals associated with the integrated circuit are sort of encapsulated in silicone. So they're not coming in direct contact with the body. So toxicity issues are not that important there. For the electrodes that do need to contact the skin to measure ECG or EMG, if you're not doing it with a capacitance approach, there's another opportunity there. You have to use metals that are compatible with the skin. So if you have jewelry, it's gold. Those kinds of noble metals are good choices, and so we use those. For transient electronics, it's a little bit different because the ultimate fate of the metal is to dissolve in interstitial fluids or cerebrospinal fluid, depending on where it is in the body. We have looked at magnesium, zinc, iron, and tungsten. Magnesium has already been explored for degradable intravascular stents. They're not an active piece of electronics, but there is some base of data around biocompatibility of magnesium in that context. For a stent, you're actually using sort of almost bulk quantities of metal, so the amount of magnesium is much, much higher than we have in our circuits. Magnesium can be processed pretty easily, so we like magnesium. Tungsten has the attraction that it's already used in commercial integrated circuits, not for all the wiring, but for the via plugs. So, and tungsten has also been explored to some degree in terms of its biocompatibility. It also undergoes hydrolysis to form a water-soluble product. So those are the metals we like to use at this point. And we've done a lot of toxicity studies at the level of individual cell-based assays as well as animal tests, and we haven't seen any adverse effects of these
Joe,
materials.
you're going to have the penultimate question, and Josh, we're going to close with you.
My name's Joseph Ayers. I'm from the Marine Science Center. I was wondering if you considered the interface between stem cell biology, organic electronics, and synthetic biology in terms of making personalized medical devices.
Yeah, I think it's a great question. I would make the more general comment that what we have done in terms of interaction of our devices with biology is incredibly primitive. I think there are a lot of opportunities to go far beyond measuring electrical activity, stresses, strains, temperature. That's kind of what we're doing, physics-based measurements. I think ultimately if you can exchange fluids between the device and the biology, you can qualitatively expand the level of interaction, the level of measurement capabilities. We've thought about using these devices as sort of soluble tissue scaffolds that you could use not only as a mechanical construct, but a construct that could do measurement and also electrical or mechanical stimulation to control how cells are differentiating. So I can't give you specific things that we want to do, but I can remark that there's a tremendous range of opportunities there that we really have. We're only scratching the surface on that. So I think it's a very good suggestion and a direction for future research.
Josh, I know you have many questions. We're going to have time for one, and afterwards, we're going to send all the questions via email to John. No, but go ahead.
Does your technology bring us any closer to a miniaturized blood pressure monitor?
That's a great question. I think being able to monitor blood pressure continuously would be a hugely valuable capability. So what we can do right now is we have pressure sensors that can integrate into these epidermal patches, and you can measure very subtle surface displacements associated with pulsatile flow of blood through near-surface arteries. So you can measure pressure wave velocity. You can do arterial tonometry at very high precision. So you can measure not only the pulse, but also the reflections and the echoes associated with those pulses. You can correlate that to blood pressure. So if you're willing to do a calibration against a cuff-based measurement of blood pressure with this kind of surface pressure measurement, then you could track changes relative to that calibrated value over time. Currently, the devices themselves don't yield in themselves an absolute value of blood pressure. They require a calibration. But I think it's an outstanding question. It's something we've been thinking about a lot. So we've made progress in that direction, but haven't fully solved it in the sense that we need that calibration step.
Well, John, when you were talking about the advantages of having Bell Labs and the advantages of being in a university, under the leadership of our provost, we look at it in terms of use-inspired research, and then we quantify success not only by the publications and the citations, but also by the impact. So this is another way of saying you'll always be welcome here. There is a natural fit, and thank you for being with us.
Appreciate that.
Thank you.
Thank you very much.
Thank you. Thank you, John. Thank you. Great job. Outstanding. Thank you.